The recent advancements in large language models have significantly improved code generation, yet subtle errors still hinder the success rate of this generated code, often necessitating human intervention, particularly for more complex issues. Traditional debugging systems typically view the entire program as a single unit, missing out on addressing errors at various levels, from basic syntax issues to more intricate algorithm problems. This paper introduces the multigranularity debugger, MG which performs hierarchical debugging by breaking down faulty code into a tree structure that focuses on different levels of error. It works by analyzing and fixing these errors in a sequential manner. To enhance testing of each code segment, researchers created a simulated Python executor design to track execution and variable states for accurate error identification. Experiments showed that MG Debugger significantly outperforms current systems, achieving notable improvements in both accuracy and repair success rates, while effectively addressing bugs across various types and difficulty levels, showcasing its strength and versatility. Method.
Hur man väljer en BPT.
In this section, the authors detail their methodology, focusing on the MG Debugger framework and its components. The effectiveness of this debugging system is evaluated through different scenarios against the human eval and MBPP datasets, employing the DeepSeek Coder V2 Lite model. Key metrics such as accuracy and repair success rate are crucial here, providing a numerical reflection of the debugging performance. The analysis begins with the fundamental breakdown of MG Debugger, highlighting its primary functionalities. These functionalities include hierarchical code decomposition, simulated execution by a large language model, LLM, and the generation of test cases aimed at subfunction debugging. Each of these components plays a vital role in improving the system's overall effectiveness. A noteworthy finding from the results indicates that the hierarchical debugging strategy significantly impacts performance. When this component is removed, the repair success rate drops from approximately 76.3% to 52.6% on human eval and from 39% to around 33.5% on MBPP. This data illustrates how hierarchical debugging enhances the system's capacity to systematically detect and resolve issues at various levels of code complexity. Moreover, both LLM simulated execution and test case generation contribute significantly to debugging efforts, highlighting the synergistic relationship between these components and the hierarchical approach. The detailed interplay of these strategies reinforces the design decisions made in developing MG Debugger. Debugging different types of bugs. The methodology proceeds to examine how effectively MG Debugger addresses distinct bug categories. The human eval fixed dataset is specifically employed for this evaluation, categorized into 6 types of programming errors: value misuse, missing logic, excess logic, operator misuse, variable misuse, and function misuse. The clear differentiation of these categories allows for a robust analysis of the debugging capabilities. The performance metrics reveal that MG Debugger consistently surpasses alternative methods in overall accuracy and repair rates. Particularly impressive is Debugger's achievement of a 97.6% repair success rate across these categories, with perfect success in all but the value misuse category. This is a remarkable feat, demonstrating the system's proficiency even when presented with a diverse set of bugs. In exploring the nuances of each bug category, MG Debugger emerges particularly effective at resolving bottom-level issues like missing and excess logic. Missing logic occurs when crucial code is left out, while excess logic involves redundant code that can create confusion. Traditional debugging approaches often fail to tackle these specific issues effectively because they tend to view the code as a whole. In contrast, Debugger's hierarchical decomposition strategy allows it to target precise aspects of the code, enhancing bug identification and correction capabilities. Thus, the results showcase Debugger's robustness and effectiveness across various programming errors, underscoring its versatile application in real-world coding scenarios. In this continuation of the method section, the authors delve into several vital aspects of their experimental approach, particularly focusing on the effectiveness of their debugging tool, MG Debugger, in comparison with other methods. The initial discussion centers around the impact of code length on debugging performance. Code snippets from the human eval-fix dataset are categorized into short, medium, and long groups, ensuring balanced sample sizes. The analysis reveals a consistent trend. As code length increases, debugging effectiveness tends to decline due to heightened complexity. Notably, MGDebugger maintains superior performance across code lengths, showcasing its robustness in tackling both straightforward and intricate code snippets. Moving on, the impact of debug attempt subsection investigates how the number of debugging attempts influences the outcomes. The authors note the significance of iterative debugging, where consecutive attempts can fine-tune corrections. They measure debugger's performance across various attempts, revealing that while many other methods plateau early, MGDebugger continues to improve, indicating its capability for ongoing refinement. This iterative improvement illustrates debugger's potential for effectively addressing complex debugging tasks through multiple iterations. The final component of this section is the case study, which provides a qualitative analysis demonstrating MGDebugger in action. The example illustrates how MGDebugger successfully identifies and rectifies bugs that alternative methods fail to address adequately. The case study showcases a particular code snippet incorporating the call-it sequence. Here, while other methods amend the noticeable bug, they inadvertently introduce new issues, missing crucial elements like the final one in the sequence. MGDebugger distinguishes itself by breaking down the problem into distinct subfunctions, allowing for more precise debugging and ensuring comprehensive error correction. This structured approach exemplifies debugger's superiority in addressing multi-step problems, ultimately leading to improved clarity and correctness of the code. The authors emphasize that this not only resolves the original bugs, but also enhances the overall quality of LLM-generated code. Preparing to lead into the experiment section, this part lays a foundational understanding of the methods and their performance, highlighting debugger's promise in the realm of code debugging. Experiments. Setup. In this study, we evaluated the performance of 3 prominent large language models, LLMs, for tasks related to code generation and debugging. The models include CodeQuen 1.5 with 7 billion parameters, DeepSeek, Coder, V2, Lite with 16 billion, and Codestral, the largest at 22 billion. Each model's implementation details are documented in the supplementary material. We utilized 3 benchmark datasets, Human Eval, consisting of 164 programming problems, MBPP with 500 problems, and the Human eval-fix dataset featuring 164 buggy functions categorized into 6 distinct error types. This categorization aids in understanding the challenges faced during code debugging. For evaluation, we adopted 2 key metrics: accuracy, defined as the ratio of correctly generated code samples that pass all test cases, and repair success rate, RSR, which indicates the proportion of buggy samples successfully fixed. We positioned MGDebugger against 8 established methods, ranging from basic debugging strategies to more advanced techniques that leverage external feedback mechanisms. Main results. The experimental outcomes reveal that MGDebugger consistently surpasses existing debugging approaches across all models and datasets. Specifically, it recorded substantial accuracy gains, achieving an improvement of 15.3% to 18.9% on Human Eval and 11.4% to 13.4% on MBPP. These enhancements are particularly striking when juxtaposed with methods like self-debugging and reflection, which showed lower performance despite their similar frameworks. Debugger's exceptional performance, notably a 94.5% accuracy on the Human Eval dataset with the larger models, demonstrates its effectiveness even without prior task-specific retraining. This high score underscores the strong inherent debugging capabilities of larger LLMs when integrated with debugger's methodology. Moreover, its ability to achieve an RSR of 41.1% with smaller models emphasizes its versatility and robustness. Ablation study. To comprehensively understand the influence of different components within MGDebugger, an ablation study was performed. This involved methodically disabling key elements of the model to gauge their individual impacts on overall performance. The results will help clarify which components contribute most to debugger success, while also validating the rationale behind the design choices made during its development. In summary, The experimental findings provide compelling evidence of MGDebugger as a powerful and adaptable solution for enhancing debugging processes within LLM-generated code. In the conclusion of this paper, we presented MGDebugger, an innovative hierarchical code debugging framework adept at addressing bugs at multiple granularity levels. By structuring complex code hierarchically and employing targeted testing along with simulated execution through large language models, LLMs, MGDebugger effectively identifies and rectifies a range of bugs, from syntax errors to logical anomalies. Comprehensive experimental results underscored Debugger's superior performance compared to existing methods, particularly in managing intricate logical errors and longer code snippets. The implications of this research paved the way for further advancements in code generation and debugging strategies, suggesting potential developments for tackling more complex coding environments like multi-file projects. Integrating MGDebugger into self-training systems could enhance model performance iteratively, promoting a richer interaction between code generation and debugging processes. This concluding insight marks a significant evolution in automated programming and debugging methodologies, emphasizing the transformative impact of hierarchical frameworks on managing code complexities.